Everything you thought you knew about trigonometric functions? Well, get ready to have that all turned inside out. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking all of our trigonometric functions and inverting them, which, as you can guess, is super fun. Inverse trigonometric functions work just like any other inverse functions. If you need a primer on inverse functions, you can check out the video here. But inverse functions in general undo each other. So for instance, the cube root of x cubed is equal to x. The cube root undoes the cube function. Similarly here with trigonometric functions, arc sine of sine is equal to x. The arc sine function undoes the sine function. In general, inverse functions give us this formulation: f of inverse f of x is equal to x. Just as we have 6 basic trigonometric functions, sine, cosine, tangent, cosecant, secant, and cotangent, we have an inverse function for each of them. So we have arc sine for sine, arc cosine for cosine, arc tangent, arc cosecant, arc secant, and arc cotangent. Now those last 3 are a little less common than the first 3, but sometimes you encounter them, and we'll look at them briefly today. But the main ones we're going to focus on are arc sine, arc cosine, and arc tangent. Just a note on notation here, we can either say arc sine of x, or we can say inverse sine of x, where the inverse sign has this superscript -1 above it. We can do the same thing with arc cosine and the same thing for arc tangent, and the other 3 as well. Now we have to be careful with this second notation here because we don't want to confuse it with reciprocal notation, which would be denoted like this. And remember, when I write, say, sine in this way, I get the cosecant function as opposed to the arc sine function. So just be careful with that notation. So, inverse trigonometric functions, how do they work? I think the best way to think about them is to, when you encounter them, to ask yourself the question, what angle gives me the trigonometric ratio in the parentheses of the inverse function? So for instance, if I am given this, the arc cosine of -1 is equal to what? Well, I ask myself the question, what is the angle that has a cosine of -1? Well, that one's pretty straightforward. It's just pi, or 180 degrees. Of course, there are infinitely many solutions to that question. We'll come back to that in just a minute. Now, inverse functions look a little bit funny because of the way that they're defined. Remember that functions can only have one output for any single input. So there are very specific intervals on which inverse functions are valid. In order to figure out the domain on which an inverse function can be valid, we take the horizontal line test of the original function. So if I draw a horizontal line straight through sine, I get this. It fails the horizontal line test infinitely many times. That's a lot of failure. So, in order to define our inverse trigonometric functions, we need to define them on very specific intervals. If you type the arc sine function into your calculator, say if you have a graphing calculator, you'll find that if I type in arc cosine of -1, I'll just get pi. But I know that there are infinitely many solutions to this problem. So there is a solution of -pi, there's a solution of 3 pi, of 5 pi, of 7 pi, and so on. Why aren't those given to me by my calculator? Well, that's because the inverse trigonometric functions are specified on very specific intervals. Recall that the domain of cosine is all real numbers and its range is from -1 to 1, inclusive. Now, if I take the graphical representation of the inverse of that function, I flip that function across the line y is equal to x, and I would get this graph. But if we take a look at this graph isn't a function. It doesn't pass the vertical line test. So we restrict this inverse function, which is equivalent to arc cosine, to an interval on which it passes the vertical line test. We could define arc cosine along any interval where it passes the vertical line test, and that corresponds to any half period of the function between 0 and pi on the y-axis. Now we could define this function along any interval of pi along the y-axis, so 0 to pi, pi to 2 pi, 2 pi to 3 pi, etc. But because of the way the unit circle works and some other conventions with trigonometry, we define the arc cosine function from 0 to pi as its range. Now, as we can see, if we define this function along that range, we get a unique output for every input of this function. In a slight digression, let's take a look at the types of problems that could be asked on an inverse trigonometric function problem. For instance, this one here. Cosine of x is equal to 1/2. Solve for x. And this one here, the arc cosine of x is equal to 1/2. Again, solve for x. In both these problems, x is an angle, and it's the angle we want to find in each of these problems. But each problem asks a slightly different question. The first question says, given that an angle has a cosine of 1/2, what could that angle be? And so there are infinitely many solutions to that problem. There is pi over 3, there is 5 pi over 3, 11 pi over 3, and so on. And there are two generalized solutions to this problem, here and here. The second question asks this question. What is the arc cosine of 1/2? Well, that, because arc cosine is only defined on the interval from 0 to pi for its range, that means there's only one solution. That solution is pi over 3. 5 pi over 3, for instance, doesn't exist along that range, and so it can't be a valid solution to this second problem here. So even though we might use the arc cosine function on our calculator to solve number 1, and we might use the unit circle to find infinitely many solutions for angles that have a cosine of 1/2 to solve number 2, there's an infinitely many solutions to number 1, but there's only one solution to number 2. Okay, so let's take a look at arcsine now. Arcsine is defined again on a domain from -1 to 1, but its range is defined from -pi over 2 to pi over 2. As we can see, this corresponds to a half period of sine, just like arc cosine corresponded to a half period of cosine, or an interval of pi. This range for sine corresponds to the fourth and first quadrants. These are two quadrants in which the sine is negative in the fourth quadrant and the sine is positive in the first quadrant. Arctangent works similarly. It is defined between the range -pi over 2 to pi over 2, non-inclusive, because remember, the tangent function approaches -pi over 2 and pi over 2 at those vertical asymptotes. Its domain is all real numbers, however. And of course, the arc reciprocal functions are super fun too. If we take a look at arc cosecant, for instance, here, that is the inverse of the reciprocal of sine. Arc cosecant looks like this. It has a domain from -infinity to -1 inclusive, union 1 inclusive to positive infinity, and its range is from -pi over 2 inclusive to 0 non-inclusive, union 0 non-inclusive, to pi over 2 inclusive. You'll see that this is not a continuous interval. We actually have a horizontal asymptote that cuts right through the function. But it turns out that there is no continuous interval along which cosecant passes the horizontal line test, and therefore there's no continuous interval along which the arc cosecant passes the vertical line test. And so we are forced to use a non-continuous interval here. Like the arcsine function, the arc cosecant function will give angle values in the fourth and first quadrants. Arcsecant, the inverse of the reciprocal of cosine, looks like this. As you can see, it's actually a flip and a translation, or a shift, of the arc cosecant function. It's defined along the same domain as the arc cosecant function, but the range is from 0 to pi over 2, non-inclusive, pi over 2 to pi, inclusive. And like the arc cosine function, the arc secant function will give answers that are angles in the first or second quadrants. Finally, the arc cotangent function. Its range is from 0 to pi, both non-inclusive. But its domain is all real numbers, just like the arc tangent function. Inverse trig functions have some limited utility, and they're mostly used to find the angles for which a given trigonometric ratio exists. Now, they also show up in some unexpected places, for instance in calculus when solving certain integrals. Next time we'll take a look at this problem, but in the meantime, why don't you try it out yourself? Given two circles that are centered each on either the arc sine function or the arc cosine function, such that the endpoints of each of those functions lie on a diameter of their respective circle, then what is the intersection point, or points, of those two circles? You'll need to use the definition of a circle, which is x minus h squared plus y minus k squared is equal to r squared, where r is the radius of the circle and h comma k is the center point of the circle. Try it out yourself, and I'll see you in the solution.